All right, so today we're going to be talking about waves, and we're actually going to be transitioning away from our usual routine with these notes of learning about a definition, learning how to calculate it, and going through a practice problem. In this video, we are only going through vocabulary because many of you might not be familiar with some wave vocabulary. So that's what we're going to do today. So again, our topic is on waves. Our objective is to be able to define and describe different parts of a wave. And the essential question for us to answer in the summary at the end of our notes after watching this video is how can we describe the motion of a wave? So let's just start with the very basics and talk about what is a wave. I'm going to try to fit this all on the screen here. Okay. So what is a wave? A wave is the transportation of energy without the transportation of matter from one location to another. So we'll kind of talk about what that really means, but a wave is simply a means of transporting energy without actually transporting a substance. A wave can also be described as a disturbance or an oscillation. So let's talk about what an oscillation really means really quickly. So an oscillation is movement back and forth at a regular speed. So if you all have ever, gone on a swing set, this is that's an example of oscillatory motion, right? So on a swing set, you are moving back and forth, right? You might have oscillatory motion just of a particle in a wave moving back and forth. So that particle would move over here, and then it'd move over here, and then back over here. That's another example of oscillatory motion. So we are going to talk about what that means in the context of waves in this video. But all it really is just movement back and forth at a regular speed. And I will highlight that also. So that's one of our vocabulary terms for today. Okay, and then I will also scroll up and highlight this part because this is our, this is our wave definition about what a wave is. Okay. All right, so we actually have two different types of waves. We have such things as mechanical waves and electromagnetic waves. So these are our two different types of waves here. Now, mechanical waves, the main difference between mechanical waves and electromagnetic waves is that mechanical waves must have a medium to travel through. In other words, they must have some sort of substance to be able to transport that energy. So for example, ocean waves are an example of mechanical waves. They transfer their energy and transport that energy through water. So they have to have that substance of water to be able to transport that energy. Sound waves are another example. This is how we hear sound in water or in air. That water or air is using those mechanical waves are using water or air to transport sound. In contrast, electromagnetic waves can travel either in a medium or a vacuum. So visible light is the best example I can think of with electromagnetic waves that you might be familiar with, right? We see light in the water. We see light in the air. Those are both examples of mediums. So they have substances. They've got molecules in them. But we also see light in space. And space is a vacuum. So space does not have any sort of material in it, unless you are on a planet, unless you're in a spaceship, right? So this is an example of an electromagnetic wave. So it can travel either in a medium, right, on Earth, through air, through water, or it can travel in a vacuum in space. All right, so now let's get into what a wave might look like. So we have two different ways, two different appearances of waves. So we have something called a transverse wave, where particles of the medium vibrate perpendicular to the wave's motion. So what you're seeing here with a transverse wave is it looks like it is really traveling, and it has kind of this motion. But really what's going on is that the individual particles, and I will zoom in so you all can see this better, the individual particles are actually just moving up and down, and they're oscillating. They're moving up and down at a standard speed, whereas the wave itself looks like it might be moving to the left or right. The particles are really only moving up and down. So that is what a transverse wave is. Now, in contrast to a transverse wave, we have longitudinal waves. Longitudinal waves are when the particles of the medium vibrate in the same direction of the wave's motion. So we see that wave moving in this direction here. And in addition to that, the particles are also moving parallel to that direction. So they're kind of shuffling back and forth in the direction that the wave is moving. So again, those particles are oscillating as well. All right, so that's kind of breaking it down for what a wave might look like. Now we can get into how we could describe a wave's motion. So if we wanted to describe a wave's motion, we have two different ways of doing so. The first thing we could talk about is frequency. Now, the frequency is the number of waves that passed a fixed point over a certain period of time. So when we talk about number of waves, we are thinking about wavelength, which we'll get to in just a moment. But you can see the difference between something that is low frequency and something that is high frequency. You see all these little peaks for a high frequency wave we see a lot more of those. So that's what I want you to think about when we think of wave frequency, is the number of peaks passing this little fixed point here, and I'll highlight it here. The number of little peaks passing this fixed point over a certain period of time. So this low frequency wave is really kind of stretched out. There's not going to be as many peaks passing this point in a fixed amount of time as there would be, and I'll label that here, right? As there would be high frequency wave with the number of peaks passing that point. So another way we could describe waves is through their period. So the period is actually described as the time it takes for a wave to complete one cycle, so one wavelength. So when we think about wavelength, and we'll talk about this in just a moment, we are thinking about when the wave resets. So its starting point and ending point are in the same position. So this is one wavelength right here. So you notice it starts in this, what we call a trough of a wave, and it ends in this trough of a wave. So that's how we kind of break it up and measure the length of a wave. So that is one wavelength. Right. Last thing I will add here is about frequency, and I will kind of star this because this is one of our key points. And we'll get to this a little bit more when we talk about electromagnetic waves and the electromagnetic spectrum, but high frequency waves have a higher energy. So the higher frequency means the wave has a higher energy. So that's just a key point to keep in mind. We will return back to that point when we talk about light and we talk about the electromagnetic spectrum, but just something to keep in mind about how frequency correlates with the energy that a wave is transporting. Okay. All right, so now let's break it down and talk about the different parts of a wave. So what I have drawn for you is a standard transverse wave. And with this transverse wave, I've drawn this red line to mark the middle of the wave. So I want you to kind of think of this red line as ground zero. The wave travels above zero and then below zero along this path. So when we talk about the different parts of a wave, we can measure some of these different parts, right? So the amplitude, or also what I kind of like to refer to as the height of the wave, describes the strength or intensity of the wave. So we calculate this amplitude by measuring the height of the wave from this baseline, this red line, to the top peak of the wave. So I'm going to just kind of write, I want to make sure that's here. Our amplitude is the height of the wave. Okay. Another thing that we have talked about that you all have already learned about just when we were talking about period and frequency is wavelength. Now, this is going to be an important vocabulary term for you all to remember because it will be used for our wave calculations when we get to that. The wavelength is the distance between two identical points on a wave. In other words, the wavelength is one cycle. So what we're thinking about when we are talking about wavelength is we want to know when that wave returns back to its kind of initial position. So this is one entire wavelength here, right? So it starts at this position, it goes up to its highest peak, then it actually goes down, so it's still not in that same position, and then finally it returns back to this center point. So this is the entirety of one wavelength here. So you can see we've kind of highlighted it. That is one wavelength. All right. Next, we'll talk about the crest, which you all might be familiar with, because if you've ever been to the ocean or the beach, we talk about the crests of ocean waves all the time. The crest is the highest part of a wave in its cycle. So it is literally how high the wave gets throughout its single cycle. So again, when we talk about ocean waves, we refer to crests. That kind of gives us the idea of, how high that ocean wave might get. All right. And then our trough, and I know this is a weird spelling of a word, but this is pronounced trough with kind of an F sound at the end, right? Is the lowest part of a wave in its cycle. So we got the crest and the trough kind of as two contrasting points on a wave. All right, so kind of zooming out again so you all can kind of see everything you've learned in this video. This is all of our wave vocabulary, kind of breaking down the basics of what a wave is and how can we use this vocabulary to describe a wave's motion. So that is what I would like for you all to answer in a 1 to 2 sentence summary at the bottom of your notes about what you learned from this video today. And I look forward to discussing this more with you all in class.